My name's Leo and I'm a boat builder and a sailor, and with a lot of help from my friends, I'm on a mission to rebuild and restore the 112-year-old classic sailing yacht Tally Ho. Now this video is going to be all about stability in relation to sailing vessels and in particular to Tally Ho. It's going to be a little bit different from my normal videos. It's going to be a lot more talking, it's going to be a bit more technical, and that's partly because I've been away for a month, and so no one's done any physical work on the boat for a month. But shortly before I left, I had a visit from an old friend, Jack Gifford, who is a naval architect, and he stayed here for a week, did a lot of work on Tally Ho's stability calculations.
I'm Jack Gifford. I'm a naval architect based in the UK. I live in Cornwall with my wife Alice. Yeah, I met Leo back in 2013 when I moved to Cornwall from the north of England for a big classic yacht restoration project, and I met Leo as a budding young boat builder, and it's been great. We've been in touch ever since. So the opportunity to come out and see him and his project was fantastic, and obviously it's very familiar territory with me. I'm used to seeing projects like this. A lot of my work is involved in classic yacht restoration and refit.
So I'm going to attempt to explain the very basics of sailing vessel stability from the perspective of myself, a relatively uneducated sailor, in a way that I hope will make it understandable in a practical sense for people with no background in this. So if you're a naval architect, you're going to find this explanation lacking and probably incorrect, but there we go. So basically stability is all about two theoretical points inside the 3D space of a vessel, and one of those points is called the center of gravity and the other the center of buoyancy. So right now we're going to focus on the center of gravity, and so that point is quite literally the center of the mass of the vessel. So say the vessel weighs 30 tons. If you imagine that 30 tons was completely equally just distributed, then the center of that area, more or less, would be the center of gravity. Because the weight's not evenly distributed, that point may be further forwards, further aft, or higher or lower than the actual center of the area. Now, because the center of gravity is a point in a three-dimensional space, we can think of it in terms of those three dimensions. Now, the first dimension would be from port to starboard, and we're going to assume that the center of gravity is on the center line for theoretical purposes, so we're going to disregard that dimension. So we've got two left. The next one is the longitudinal or fore and aft center of gravity, and that is how far back from the front of the boat is that center of mass. Now the third dimension is the height, the vertical center of gravity. So how high up from the bottom of the keel, for example, is that point of center of mass. Now the longitudinal center of gravity is important because it affects the trim of the boat, and that affects how the boat looks and how it performs. So obviously if the center of mass, center of gravity, was too far forward, the boat would be bowed down in the water, it would look odd, it would sail odd, and vice versa. If the center of gravity was too far aft, it would be stern down in the water, and again it would look and sail oddly. However, even if the boat is a little bit bows down or stern down, it's probably not going to be terribly unsafe. It's just not going to be performing quite right. Now the vertical center of gravity though is arguably more important, so the height of that center of gravity from the bottom of the keel, because that is what really affects the stability of the boat. It's the height of that center of gravity in relation to the center of buoyancy, which controls how fast the boat is going to want to come back up to its upright position, and even at what point it's going to just not come back up at all. In this case, we have a boat that's already designed and built. We can't really affect the center of buoyancy. So again, we're just looking at the center of gravity, but it is the relationship between the two of those things that actually affects the stability. Now the most important thing in terms of safety is obviously not to have that center of gravity too high, because if it is too high, the boat's going to be less stable, and in practical terms that's going to mean that it could get knocked over by a wave or blown over quite easily, and it might not come back up. So that's an obvious problem for safety and also for coding issues and so on. So assuming that the centre of gravity is low enough that the vessel is theoretically safe, there's still a range of where the centre of gravity can be, and depending on where it is, the boat will have different characteristics. And the words we use to describe those characteristics in a sailing vessel is tender and stiff. And so you may think that the centre of gravity should just be as low as possible, but that's not always the case with a sailing vessel. If the centre of gravity is very low, that is what we call a stiff boat, and that has advantages and disadvantages. So the advantages would be that it's very stable, it can probably take a lot of wind, a lot of weather, but the disadvantages would be that it would tend to have a very uncomfortable, violent, jerky movement because it's always trying to get back upright very quickly, so it can be a very uncomfortable boat to sail in. And also when there's light wind, when there's not a lot of wind, the boat might actually not heel over at all, and sails actually have to be a little bit heeled over to work properly, to work efficiently. So in a boat like Tally-Ho, for instance, which is a heavy boat as well, if she was too stiff, if the centre of gravity was too low, in light winds she might struggle to really sail at all because the boat would just be bolt upright in the water. She wouldn't have that small amount of heel which is going to make the sails work properly and get the boat moving. On the other hand, if the centre of gravity is too high within that safe window, then we would say it's a tender boat. Again, that has advantages and disadvantages. It's going to be a more comfortable movement. It's going to move better in very light winds, but it's going to be a bit more unstable. In heavy winds, it might heel over too much, too quickly, and so on a boat that's tender, you have to reef the sails, reduce the sail area early so that there's less canvas taking the force of the wind. So there's not necessarily a perfect point for the vertical centre of gravity. It depends on the type of boat and it depends on what it was designed for. Tally-Ho was designed as a comfortable cruising yacht, and so she had quite a lot of interior ballast, which was very fashionable at the time because it was fashionable at the time to design these boats to be quite tender because they were more comfortable, and because they were heavy boats, they tended to sail better in light winds if they were a little bit tender. Now I mentioned the centre of buoyancy earlier, and that would be more relevant if we were designing a boat, but because we don't have any control of the hull shape at this point, it's not quite so relevant. But basically the centre of buoyancy is the centre of the area of the boat which is underwater. And so when the boat heels over, the area of the boat that's underwater changes, and so the centre of buoyancy changes. And it's the distance from the centre of buoyancy to the centre of gravity which makes what's called the righting arm or the GZ lever, and that is what forces the boat to come back up to its position of equilibrium, or if it's gone too far, go down to its inverse position of equilibrium. Essentially, the lower the centre of gravity, then the bigger the righting arm, the distance between the centre of buoyancy and the centre of gravity when the boat is heeled over. Well, I hope some of that makes sense. It's a gross oversimplification and I probably got some of the terminology wrong, but hopefully it portrays the concept pretty well in relation to a boat like this.
So I'm currently taking a year out of real life, if you like, and my wife and I have recently just sailed across the Atlantic from England, and it was whilst we were on that journey Leo got in touch, mainly just to catch up, and then he was saying that he has some work coming up where he would like to look a bit more in detail at the stability aspects of Tally-Ho. The goal when I got here and in conversations prior to that with Leo was that he really wanted to get Tally-Ho floating back on her original lines as designed by Albert Strange. So the priority was to assess her original condition, assess the changes that have been made, and make sure that as Leo goes forward we know where to put the ballast and how much ballast to put in to make sure that we achieve that original waterline. The overall weight of the boat and the position of that weight in the boat has a direct impact on the design of the spars. The load that comes from the righting moment of the hull directly translates through the shrouds into the spars. So when designing the spars, we need to make sure that they're strong enough and they're stiff enough to counteract that load. And also the weight of the spars being so much higher above the waterline than everything else has a large impact on the stability of tally-ho. And also the weight of them physically between their original build and the new build can have quite a large impact on how tally-ho behaves. So part of my work here this week has been to really assess how sensitive tally-ho is to changes in rig design, and to make sure that we carry that knowledge into the design process for her new set of spars. So we've got the original design drawings, and we've got that which include that original waterline.
Yeah.
So the whole process started with me making a 3D model of the boat based on those lines.
Yeah.
And that was then honed using the lofting lines plan that you rebuilt the boat from.
Mm-hmm.
So without regarding her weight as is or doing any further calculation,
mm-hmm.
I could just take that 3D model, float it to the line indicated on the design drawing,
mm-hmm.
and that gives me the total displacement, which you and I have discussed
mm-hmm.
At length, and then it gives me the centre of gravity fore and aft,
mm-hmm.
not vertically, but it gives it fore and aft in terms of where that weight needs to be for her to float on that waterline.
So the overall goal in doing all of this work, of course, is to maintain tally-ho's original sailing characteristics. But there's really two main purposes within that of doing this work right now. And one of those is to know where we're going to need to place all the internal lead ballast, because that is going to affect where the water tanks get placed inside the bilge of the boat and therefore their shape. And the other thing which could be affected by this is the spar design, because depending on if that centre of gravity is changing, we can compensate for that by building the spars lighter with more hollow in them, or heavier with more solid timber, and so affect the centre of gravity to bring it back to where it should be originally. So we talked earlier about longitudinal centre of gravity versus vertical centre of gravity, and the process for figuring this out starts with working out the longitudinal centre of gravity, and that's relatively easy because we have the lines drawings. So Jack was able to make the 3D model of tally-ho, and a piece of software then, just by having that 3D model and knowing where the waterline should be, can calculate two things: the overall displacement of the boat, which is the amount of water that it displaces by floating to that line, and that amount of water obviously corresponds to the weight of the boat. So the displacement really means the weight of the boat, and that program can also calculate where the center of gravity should be in order to be in equilibrium with the center of buoyancy, in other words, for the boat to float level and true on her lines. So very quickly, we've worked out the displacement of the boat and the fore and aft center of gravity. We can't, however, work out the vertical center of gravity by just using the lines drawing and the software. So in order to estimate the vertical center of gravity, we basically have to make a weight table or a weight spreadsheet. And so Jack has estimated the weight of every part of the original boat down to quite extraordinary detail. And so the position and the weight of all the structural elements of the boat and everything that was likely to be inside it. And that when you plug it all into the computer, that gives a vertical center of gravity of where we think the original center of gravity was. Once we've got that, we basically just have to do the same thing for the rebuilt boat. And so there are changes in the weights, both the structure of the boat and the things which are going to be inside it, because of different types of timber that we used, different scantlings, different dimensions in some areas. And so again, Jack has made a really remarkably detailed spreadsheet showing the weights of all the structural parts of the boat and all the things that we're going to put in the boat and their location. And then what that gives us is an estimate of where the new center of gravity will be in different conditions, depending on how much internal ballast is put in and where it is situated and how heavy the rig is and so on. So basically, by comparing these two models then, the model of the original boat and the model of the rebuilt boat, we're able to work out if the longitudinal centre of gravity is going to be in the right place, what we have to move and how much we have to move it in order to adjust it or get it to the right place, and the same thing with the vertical centre of gravity, if the boat's going to be too stiff or too tender in different rebuild scenarios. So for example, if we were to put solid spars in, how that would affect it. If we were to put completely hollow spars in, how that would affect it. And then in terms of longitudinal center of gravity, where we have to place the internal ballast to make sure she's trimmed properly too.
Yeah. So those key changes being increased scantling weight,
yeah,
the different types of timber, some of the choices that you've made for, you know, durability and strength. The shift in ballast, you know, the different external ballast keel. And then obviously the rig is going to be a bit lighter, well, a fair bit lighter, because of the change from the original, what we suspect was Oregon pine heavy, into aircraft grade Sitka spruce, which is beautifully light. The difference between the original condition and the new condition, we can, our main buffer zone, if you like, is that large amount of internal ballast that we know she originally had. So in the original drawings, there's a beautifully vague line, as you know, that just says approximately 8 tons, with no real indication as to where it was or actually how much they used. But we know we've got roughly that amount to play with. So any additional weight we can take out of that, and any additional trim caused by, you know, your diesel tanks aft or your washing machine up forward, and the change in the external ballast keel, we can use that internal ballast to try and mitigate that.
Yeah,
basically. And also the rig itself, in getting lighter, will help reduce that effect as well, because although the rig is not one of the heaviest items on the boat compared to the ballast, for example, it is really far above the waterline. So any small change in the rig can be amplified into, you know, serious amounts of weight down below, just because it's so far from the boat's centre of gravity.
Yeah.
So the weight estimate spreadsheet is essentially just a big table of masses and levers around a central point. So we're just totaling the effect of all of these different items, all the items we can think about. The more items we can capture with a degree of detail, the better, so that the end result just gets more and more detailed.
So basically, as we've been going through this process, we've discovered some really important and interesting points. It does seem that adding volume to the external ballast keel was a really good idea in relation to how much interior ballast we're going to have and where it's going to go. However, because the external ballast keel is generally nearer the back of the boat than the front of the boat, by shifting more weight down into it, we've actually moved the centre of gravity a bit further aft. So there is a risk of the boat being stern down. And so what that means is we're just going to have to put a little bit more of the internal ballast further forward than we may have done otherwise. And it was actually really, really valuable to work that out now, because that has affected the tank placement inside the boat, and therefore the shape of the tanks, which are actually being fabricated right now. So I was able to get that information and make those changes before the tanks were actually manufactured. So that's the fore and aft centre of gravity taken care of, and it does look like we can keep the boat in trim fairly easily just by shifting a little bit of that internal ballast a little bit further forward and moving the water tanks to compensate. Now, in terms of the vertical centre of gravity, we discovered that the way that things are going with the rebuild, it does look like we're going to be in a pretty good shape. We don't have to do anything too extreme with the spars. So we're going to be building sort of semi-hollow spars, which was kind of the ideal scenario, really. We don't have to make them really crazy light and thin, and also we don't have to try and make them really heavy. The centre of gravity is looking, with the extra ballast outside the boat, it's looking like it's going to be in roughly the right place. The rig is going to be lighter anyway, because we're using a much lighter timber for the spars. So it doesn't look like we're going to have to do anything too drastic to maintain the original sailing characteristics of the boat, which is really good news, because I think that's a really, really important part of the character and the history of this vessel. All right, well, that is all we've got time for right now. Sorry this video was just so much talking, but as I said, I have been away in the UK for a month, catching up with friends and family. It had been over 2 years since I'd seen anyone, so it was a really much needed break, and it was a lot of fun, but I'm also really glad to be back and really looking forward to getting back to work. So thanks a lot for watching this video, and a massive thank you to everyone who has donated or otherwise supported this project. It does make a huge difference. It means we're able to carry on with this work, and it means I'm able to carry on making and editing these videos. So I really appreciate it. And I'll see you next time. Cheers.